So our last lesson for Chapter 1 is infinite limits, and that starts on page 80. So hopefully I've said to you before now that this week is not normal. Usually we just do 1 or 2 lessons a week. This week we've had 4, so don't judge the class by the past week. We usually only do 1 or 2 lessons. Okay, so an infinite limit is a limit where the y values increase or decrease without a boundary as x approaches c, so they approach infinity. So the equal sign is a little bit misleading to say that it equals that, but the meaning is that the limit does not exist. The infinity lets us know specifically why the limit does not exist. But we're going to go with the answer, infinity. Now, they will not have both of those on a multiple choice question. They won't have both of those answers because this implies this. So to have both of those would be ambiguous. It wouldn't be fair. So you don't have to worry about that too much. Okay. So find the real number c that is not in the domain. Determine whether the function approaches negative or infinity or positive infinity as x approaches c from the left and from the right. Okay. So just to be clear on this one, it was the absolute value of 1 over y. So the graph of that actually looks like this, and both sides approach positive infinity. Remember, we talked the other day about if one of those goes the other way, then we have an infinite discontinuity. One is approaching negative infinity, the other side is approaching positive infinity, so then we can't use this at all. We just have to say it does not exist. Okay? So first of all, find the real number c that's not in the domain. So when we see division, when we see rational expressions or functions, we know that we can't divide by 0. So that's one of the main things we're looking at. The 2 main problems we have in algebra, in math, are dividing by 0 and the square root of a negative number. So we want to, anytime we have a situation, we want to consider those 2 things. Okay, so 4, when c equals 4, then that's the number that's not in the domain of this function. So if we think about it, if we approach 4 from the left, so we have 3 over, and to the left of 4 is, for example, 3.9. Now that's just an example. I don't want to write 3.99999. So you have to be clear that you're thinking of a concept, not an actual number here. So that's going to be 3 over, and when we subtract these, we're going to get negative 0.1. And if you divide that, you get negative 30. And so if you think about it, if you keep going and you get 3.99, you would get 0.01. And if you divided that, that would be negative 300. And so if you kept getting closer to 4, like I said, 3.99999, then this is going to get much smaller. When you divide it into 3, that's going to get well, it's negative, so actually much smaller. So that's going to approach negative infinity because you have this tiny amount that you're going to divide into 3, and that's going to be an infinite number of times, and then we have the negative. So that's negative infinity. So I am a little bit worried about this video. So if we do this again a little bit from the right, that's going to be 4.1 minus 4. So that's going to be 3 over positive 0.1. So that's going to be infinity. Okay? And if we look at that, we can think about, well, what do we know about the limit as x approaches c of that function? Well, because these are different values, we're going to say that does not exist. Okay. It didn't specifically ask us about that, but I had mentioned it up there, so I want to point that out. So here, again, we can pause now. It's almost the same question, so you could pause and you could do that real fast and then compare it. So here, C is 2. If x equals 2, that's going to be dividing by 0. So if we go a little bit to the left of 2, that's going to be 1.9. So that's going to be positive 0.1. And if we keep getting closer to 2, 1.999, then this continues to get smaller, and when we divide that, that's going to approach positive infinity. All right, and down here, 1 over, if we go a little bit to the right of 2, that's going to be 2.1, and that's going to be a negative 0.1 again, similar to over there, so that's going to be negative infinity. So this was positive infinity, and this was negative infinity. And since those are different, approaching different values on the left and the right, that's also going to be does not exist. That's an infinite discontinuity. Okay. If we move down here, the value that causes us some problems is 3. So if that equals 3, we'd be dividing by 0. That'd be bad. So if we go a little bit to the left of 3, that's going to be 2, and a little bit to the left of 3 on a number line would be 2.9. Again, we're just picking 2.9 because it's a nice number to check to see what's happening. So it is going to be negative 0.1, but that's going to be squared, so that would be 0.01. And if we divided that, that would be 200. But if we kept going, 2.99, we could make it 2,000 and 2 million and 2 billion, and so that's approaching positive infinity. Now, if we go on the other side, from the right side of 3, that would be 3.1, and you can probably think about that in your head already, that that's going to be the same thing because we're squaring this, so that's also going to be positive infinity. So that one, if we asked you what's the limit as x approaches c, that would be infinity, meaning that it does not exist because it approaches infinity. Here we have negative 2. If you plug negative 2 in there, or, well, from the left of negative 2 would be negative 2.1, but we're going to square that. So that's going to be positive. So we have negative 3 divided by a small positive number. That's going to go in negative infinity times. If we approach c from the right, so to the right of negative 2 is negative 1.9 on a number line, and we're going to get 0.1 squared, but then we're going to divide that into a negative 3. So that's also going to be negative infinity. So here, if we were to ask what's the limit as x approaches c for the whole thing from both sides, we would say it's infinity because that gives us the reason why the limit does not exist. And here we do the same thing for this function. Now this function is up here, this function is up here. We could have used a different letter for that, g of x, but it doesn't really matter. So this one, they both approach negative infinity, so that's going to be negative infinity. All right, we have a vertical asymptote if at x equals c if f of x approaches negative infinity or positive infinity as x approaches c from the left or the right. So that's just kind of giving a limit approach to what you already learned about vertical asymptotes the last year or two. Okay, so I don't know if it's still chapter 2.6 from your pre-calc notes, so if you still have your pre-calc notes, you could go back and check. That's what it was when I was teaching it, I think. Might be the same book, I'm not sure. All right, so find the vertical asymptotes and removable discontinuities as functions. So vertical asymptotes are actually questions that appear occasionally on the AP Calculus exam. So vertical asymptotes would be when we were dividing by 0. So vertical asymptotes, we want to factor this. Now that's not the difference of two perfect squares, but it is the difference of two squares. So hopefully you can pause, take a second to think about what that factors to. That's going to be x, and we take the square root of that, so that'd be the square root of 5. So x plus the square root of 5, x minus the square root of 5. The numerator doesn't really factor there for us. So what we want to be careful about is if the numerator does factor, and we'll get canceling factors there, then we want to be careful because that's a removable discontinuity. But we don't have that here. So we have vertical asymptotes at x equals root 5 and x equals negative root 5. And you want to make sure you put x equals because a vertical asymptote is a line, and we want to have that on there. So what we can do here is approximate where that would be. So radical 5 is a little bit more than 2. So that's going to be over here between negative 2 and negative 3. Doesn't have to be perfect. And this will be in between positive 2 and positive 3. So a little bit closer to 2. So we have those asymptotes there. Now, going back to pre-calculus, we have some rules that will help us for calculus if we remember the rules about horizontal asymptotes. Okay, so the horizontal asymptote rule is if the degree is the highest exponent, if the degree of the numerator and the denominators are equal, then you have a horizontal asymptote at the ratio of the leading coefficients. So the ratio of the leading coefficients here would be 3 over 1. So 3 over 1, because the degrees are equal, they're both squared. So that would be y equals 3. So at y equals 3, we have a horizontal asymptote. Now, I'm not going to draw it all the way across because I don't want to give you the idea. Vertical asymptotes can't be crossed. Horizontal asymptotes can be crossed. All horizontal asymptotes do is tell us about the end behavior, what's happening at the end of the graph. It doesn't really apply to the middle. You can draw it all the way across if you want to. But all right, but we have two other cases that we should consider just as review. So if the degree of the numerator is less than the denominator, so if this is, so I could do an example over here. So if this is, well, I could do an example up here too. Ax cubed plus, everything after that doesn't matter. So if those are both cubed, whatever comes after that, because cubed dominates the value of the function. So that would be a over b. So here, the numerator is less than the denominator. So that would be something like x squared over x cubed. So the numerator's degree is less than the denominator's degree. So in that case, if you reduce that, if you think about, no, and whatever comes after that doesn't matter. So if you reduce that's 1 over x, and as you approach infinity, you're going to get 1 over infinity. Well, 1 over infinity is going to be 0. You divide 1 by a massively large number. Okay. Now here, you get, if the degree of the numerator is larger, like x to the 4th over x cubed, then you don't have a horizontal asymptote. You actually have an oblique asymptote, which would be a slanted line, which we may have one of those later. And you can get actually different kinds of asymptotes, but it doesn't get brought up very often. Okay. So back to our problem here. Now, we could do one more thing here, maybe get the y-intercept. So the y-intercept is when x equals 0. So if we plug in 0 for x here, we can see that that's negative 1/5. Okay? And so if we have 0 and negative 1/5, oh, I missed this here. That's a 3. My eyes aren't that good. I hope some of you notice that. So that's a good reason to use pencil. I do have some white out, but on a graph, that's not going to be very good. So I just noticed that as I was looking there. So disregard the further one. All right, so 0, negative 1.5 is right here. So if we plot that point. Now, if we think about x-intercepts are when y equals 0. The only way y could be equal to 0 is if the numerator was equal to 0. And that's never going to be 0 because x is squared, that's going to be positive. we can't get the numerator to be 0. So there are no x-intercepts. So since I know there are no x-intercepts, then I know this, as I move to the left, needs to approach this asymptote. And it can't approach the asymptote up here because it would have to cross the x-axis. So it has to come down. And we could do a t-table if we wanted to, but we really shouldn't need to. So those are both going to come down there like that. Now, here, I know that it's not coming up from here because, again, it would cross the x-axis, which means it has to be approaching this way. Now, there are some strange functions that actually cross the asymptote and do some weird stuff over here, but this isn't really that strange. So, there we go. And so we could mention x-intercepts. There were none, because y doesn't equal 0. Y does not equal 0. So that's why we have no x-intercepts. All right, so moving over to the next one here, we're going to factor. Rational expressions, we almost always factor. So that's going to be x and x. And negative 8 with a 2 in the middle, so that's negative, so they need to be opposite signs, so positive and negative. And 2 times 4 is 8, and that should get me a 2. I want it to be positive, so the 4 is going to be positive and the 2 is going to be negative. You multiply it back together real fast to check, and you should be good. Down here in the bottom, we have the difference of 2 squares, so that's going to factor like that. Now, when things cancel like that, that gives us a removable discontinuity. So we've already talked about that, removable discontinuity, and that's going to be at the value that canceled there, which would be 2. And then if you want to find the y value, you can plug it back in. You think about the function, y equals x plus 4 over x plus 2. That's what would be left. So if you plug 2 into there, you're going to get 6 over 4, which reduces to 3/2. So what we can do is at 2 and 1.5, we can put a removable discontinuity in right there. Okay. Now, vertical asymptotes. We do have a vertical asymptote. If we go back to that, that's going to be x equals, and that's going to be negative 2. So at x equals negative 2, let's see if I can get this one. Might need to start wearing my reading glasses when I do notes. It's getting close. Okay, so there's a vertical asymptote. And then horizontal asymptote, that was, I didn't read last time. So that's the, remember you look at the degree. So the degree of these are equal. We could do it here or here. The degrees are equal, so that's the ratio of the leading coefficients. So that's 1 over 1. So we have a horizontal asymptote at y equals 1. So we can put that in down here like that. So, and this one does have a, okay, so we can do a y-intercept and an x-intercept. So a y-intercept is going to be when x equals 0. So if we plug 0 in there, that's going to be 2. So we have a y-intercept at 0, 2, which is right here. And we have an x-intercept when when y equals 0. So y is equal to 0 when the numerator equals 0. If x equals negative 4, we'd have 0 divided by negative 2, which is 0. So that happens when x equals negative 4. So negative 4, 0 is right there. And that's the only x-intercept. So that means that this is going to have to approach that way. And then it's going to curve up here. That was a little too close. It's not really supposed to touch that line. It's just supposed to get close to it. And, okay. Here. This is going to approach that way. That's going to go through there. It has to go through the hole and that y-intercept. Okay, so that's it for the chapter. Now we want to focus on some AP questions. This describes the format of the AP test. If you're not familiar with that, I'll let you read that yourself. I don't want to use up time on the video reading that to you, so you can pause it and look that over if you want to. So here are some examples of some limit questions that have been on some past tests. So evaluate the limit. So the first thing you would do is, can I use direct substitution? But if I plug a 2 in there, I'd be dividing by 0, so that's bad. So then your first thought should be, well, maybe I can use the dividing out technique. So I'm going to factor this, and so one has to be positive and one has to be negative. That's positive, so the bigger number's positive, so probably 3 and 2, and when you check that, that works. Now this is down here, but these are opposite factors, so I'm going to factor out a -1 to deal with that. So those are going to cancel, and now I just have negative x plus 3. So I have the limit as x approaches 2 of negative x plus 3. So if we plug 2 in there now, we just get -5. So that's an AP question. So that's pretty straightforward. So now over here, the first thing that should come to mind is rationalizing the numerator, because you see a square root in the numerator. Now it's not 100%, but it's pretty good. So we're going to multiply by the conjugate. Please remember to pause these videos and try these things yourselves, not just sit there and copy me doing this stuff. It's not that helpful. Okay, so we multiply that out. We're going to get x minus 5. The middles are going to cancel. We're going to get -4. And remember, do not multiply this out down here because it's going to cancel. That's the whole point of this. So x plus 5 plus 2. Okay, so that's x minus 9, so that's going to cancel out. So this is just going to be 1, and now this is going to approach 9. So we're going to have 1 over 9 plus 9. That's a -5. That was careless of me. I had the minus there. This should also be -5. Those should both be -5. So 9 minus 5 is 4, so that's the square root of 4. Plus 2, that's 2. 2 plus 2 is 4. So that's 1/4. Be careful when you see the positive and the negative of the same thing there. That's tricky. So watch out for that. How many vertical asymptotes exist for this? So what we want to do is focus down here. So we want to factor that. So it's going to be 2 sine x and sine x over here. 2 sine x times sine x is 2 sine squared x. Now this is 1, so that's got to be 1 and 1. The middle is negative. This is negative, so they're opposite signs. And the middle is negative, so this will give me -2. This will give me +1. So when I solve these two separately, I'm trying to solve that for 0. So that's going to be 2 sine x equals -1. If we set that equal to 0, subtract 1, and then divide by 2. So we have -1/2. This one is just going to be sine of x equals 1. So if we ask ourselves, when does the sine of x equal 1? Well, that happens at pi over 2. Now, we don't even need to know that specifically. Hopefully you know it happens once, but pi over 2. Now, when is the sine going to be equal -1/2? That's the unit circle. That's the y value. That's here and here. So we could find those two values. This is pi. That's 30 degrees past pi, so that's going to be 7 pi over 6 and 11 pi over 6, but we don't need that. We just need to know how many times does it happen. So that happens twice. This happens once, so that's going to be 3 times. So I'm going to pause the video here and do another clip.